session. And I'm first going to go to the first, as it appears on the slides, the question. So let's just share the slides. Right. So the first question is regarding the equilibrium constant and its temperature dependence. So, and the person who asked the question was mostly concerned about, yes, it's okay for now, so we are going to use the Van 't Hoff equation. But what if I now have to design my reactor in CPJ or wherever I end up with? In most instances that I have noticed where people published results for reversible reactions, they actually shared the full expansion, or they did the maths in order to calculate this KC. But I'm going to give you the reference, so if you want to read it up, you can make a note of that. So just on a whiteboard, let's just see, whiteboard. So where this comes from, the temperature dependence, is from thermodynamics, of course. Oh, my word, that's ugly. Let's try again. So in your textbooks, your thermodynamics textbooks, in chapter 4, so it is, no, sorry, chapter 14, and it's given on, let me just, I made a note of the references of the page. It's page 533 to 537, and that is in the 8th edition of Smith, Van Ness, Abbott, and Swihart, your thermodynamics textbook. But what it boils down to is the following. We know del G is equal to del H minus T del S. And we know that our equilibrium constant, so this is refreshing the memories here, is equal to min del G over RT. Right, so if I now say I've got a, how do I calculate del G? Del G, therefore, is equal to del H minus T del S. And for del H at any temperature, if I now want to calculate the value at any temperature, I have to say that del G minus del G at some reference temperature is equal to, and now if I have to calculate del H, we know it's going to be equal to del H at the reference temperature, or let's just call it reference temperature, plus, and this is del Cp, that's a Cp reaction dt from my reference temperature to the temperature where I am working at. And this del Cp of the reaction can in fact be temperature dependent, because you will have an A T squared plus Bt plus C equation for each of your components, and you can actually calculate that in as a delta A and a delta B for the different components. So this is the first term, and then we've got min T, and that del S, that is generally suffice. This suffices for liquid phase reactions. For gas phase reactions, we will have that extra variable in del S. We also have to consider the delta S. How does it change with temperature? So if I want to calculate del S, it will be equal to del S at that reference temperature plus. And then I've got delta Cp of my reaction over temperature dt from the reference temperature to that final temperature that I'm interested in. This is now, of course, the standard state values. So if I now finally want to put that all together, it takes 3 or 4 pages in Smith, Van Ness, and Abbott. I need to realize that what I'm actually interested in is how does ln K change with temperature. So I'm interested in d of min del G over RT dt. And for that del G, I'm going to substitute all that different terms that I've just expanded, the one for the del H at the reference state plus del Cp dt. And for the del S, you can then, sorry, the del S at the reference state plus del Cp over temperature dt from temperature to temperature reference to that final temperature. And that everything, all that, divided by RT and then differentiated 2 dt. And Smith, Van Ness and Abbott, this is way too much writing with the limited tools that I've got available. But Smith, Van Ness and Abbott does a very detailed example on how to do that on those pages. And he breaks it down into the different sections and makes it easy, well, relatively easy to digest. But in my experience, most people who publish rate data for reversible reactions. So they will publish their rate equation for A, for instance, min K, blah, 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 and they will have the Kc, and they will have that temperature-dependent expansion already calculated on your behalf. So you should have an algebraic equation for Kc. Most people supply that when they supply the rate expressions for reversible reactions. Also to note, no, thank you. So also to note is that if I, could you please give the chapter and the page number for, okay, let me just give it again. Let me just write it out. So the chapter, and this is the 8th edition. 8th edition, it is in chapter 14, and if you need to read it up in the index in other chapters, it's just the temperature dependence of Kc, and the page numbers is page 533 to page 537. So it gives that full expansion. Right. Okay, so of course, this Kc is not the true equilibrium constant. The equilibrium constant has no units because it's actually, if you should recall, while we are now, I'm going on a tangent, I get excited when I talk thermodynamics. It is equal to the fugacity of each of the components raised to their stoichiometric number. No? So only when I've got the sum of my stoichiometric numbers equal to 0 and I've got ideal mixing, can I exactly relate Kc to that equilibrium constant. But most people who design equations for rate expressions use the Kc value, which is then of course this product of all the components, the concentrations of each, raised to their stoichiometric numbers, mostly for liquids. And for gases, they use the Kp number, which is the partial pressures raised to the stoichiometric numbers. And if you've got a reaction like A goes to B plus C, this will not be dimensionless. So it will have a concentration kind of unit, and the Kp one will have a pressure kind of unit. And of course, that will be required if I don't know whether you saw Anna's question in Ask Gillespie. That must be required if my units for R, the rate, must make sense. And that is why when we use this in reaction kinetics, we kind of used the same temperature kind of dependence, because that would still be true, but we base it on concentrations or partial pressures, and therefore we make sure to specifically indicate that beware you are not going, when you go to thermodynamics and you calculate del G over RT, and you do that whole temperature dependent thing, you are not going to get the same value for K. You may get the same temperature change with temperature. But there's a link, of course, between the partial pressures and the total pressure, so that may affect, that will be the link between your Kp value and your true equilibrium constant, and the total molar concentration and your K value will be a link between Kc and K. So I understand it can be really confusing, but in most cases, unless you want to make a thorough study of this and understand it perfectly, it is suffice to say that most papers that publish kinetics give you this Kc expansion as a function of temperature, or the Kp expansion as a function of temperature, and that is what you then use in your rate equations. All right, so more questions on this? Okay, right. So let's just go back to the slides. Right, so the next one is the question that I asked you to do. So if I close this, right, next slide. And that is when we now consider our rate equation. We consider the interest rate take place during No, definitely. So catalyzed reaction. So Gareth, thank you for your question. If I catalyze a reaction, does it necessarily say that the reverse reaction does not take place? It may be, in fact, that the catalyst is very specifically developed in order to suppress the reverse reaction. So that is often the case, but it's not necessarily true. So when people, so that Kc value, and that will be due to an absorption value or a desorption value. So the rate expression might then look completely different, because we also take cognizance of the fact that the reactants must adsorb on the surface of the catalyst, they must desorb, and they must diffuse or to or from the catalyst surface. So no, it's not necessarily true that reverse reactions cannot take place, or the reverse reaction cannot take place when I have a heterogeneous system where I catalyze it. Okay, so if I now consider this part of the slides over here, so we look at our rate equation, there. Look at our rate expression. Just get something that I know you can see. If I look at my rate expression, of course, hopefully you went through the slides, is to say that there are two things that can affect rate: temperature and concentration. Temperature and concentration. The higher the temperature, the higher the rate. But this is also true for the reverse reaction. And the higher the concentration of the reactants that contribute, that can collide and facilitate the rate, the higher the rate. Also true for the reverse reaction. If I start with none of my reactants, and I have an increase in temperature as I convert. So therefore, I've got an adiabatic reaction that takes place in an exothermic reaction. So the exothermic reaction that takes place adiabatically. With conversion, I will see an increase in the temperature. But with conversion, I will see a decrease in the concentration. And that is observable in my rate. That is why for an exothermic reaction, when it is reversible, and I start with pure reactant, I initially will, the temperature effect will win. So I noticed some discussion on Slack that says this, remember this one is the combination of K over Kc. How that will change with temperature has got nothing to do with X. It's nothing to do with the conversion or in which reactor you are. It is just the ratio of how this K naught e to the min E over RT, and my Van 't Hoff equation, that is that K C naught e to the min del H over R, and then that 1 over T relationship. So how big is this relative to that? That will affect the size of this reverse rate constant. But what is more important is that with X, with conversion, I am changing, this will go down and this will go up. And this pretty flat part here is I've got the two effects and they are competing, but the rate stays pretty much constant for this selection of X values, because as X, the temperature effect wins for the forward reaction, and then suddenly this reverse reactions concentration start to just really take over, and as soon as that starts to happen, it's almost an intense and very immediate drop down that cliff to a zero rate. Right, so the question I asked, and that was specifically for adiabatic reactions, exothermic, where I see an increase in temperature with conversion, but a decrease in concentration, and this reaction, this concentration there, is the reason why suddenly, as well as this rate that increases, that as soon as this starts to become big enough, I will have that sudden dropping down into the ocean. Of course, for a endothermic reaction, as discussed, we will not have that effect because both effects work in the same direction. So as I increase conversion, I'm going to decrease the temperature. So my rate constants will decrease, okay? But as this decreases for the endothermic reaction, this decreases as well. So I've got this extra effect that this rate is not as temperature dependent sensitive, with a decrease in temperature as my forward rate. And as the rate constants drop, I also see a decrease in that and an increase there. So both effects just contribute to the fact that I will see a steady drop in the rate until especially when I approach that equilibrium boundary, when there's a sudden decrease in the rate. So my question was, if I now have a plug flow reactor and I've got 3 different inlet temperatures. So let's just, so this is the blue, this is the colder one. Then I've got the slightly warmer inlet temperature and I've got the warmest inlet temperature. The first thing to note is that if I have the colder inlet, my reactor will run colder, and I am going to be able to achieve a higher equilibrium conversion. And you can notice that same thing for each of the 3 lines. But what I'm interested in is what is happening over here. So I'm just going to open a whiteboard so I can have more space to write. If the temperature changes, why don't you, where does it disappeared, my thought? Can't you shift the direction if the temperature changes drastically? So you see, what will cause a change in temperature? Maybe we should ask that first. So when I've got an adiabatic reaction, like that, the only reason why the temperature will change is because of this adiabatic energy balance, right? So if I increase that adiabatically, the ultimate point that I can reach is this X. So let's see what is going to happen if I can increase the temperature then as much as I want. So if I increase the temperature further here, right, why will it increase? Not because of the reaction, because the reaction wants to stop. Okay, so the only reason I can get the temperature to change once I've achieved equilibrium is by introducing some external cooling or heating. And in fact, that is what we do with equilibrium limited reactions, is to heat them or cool them up in order to manipulate where we are. So if I start up, I will not necessarily run adiabatically. I may actually, along this line, heat up or cool down my reaction in order to manipulate the equilibrium conversion. But if I do it adiabatically, I am stuck because the only source of energy is the reaction itself, and it heats itself up till the point where it's equilibrium, and then it's going to stop in that reactor, in an adiabatic reactor. Yeah, maybe I think what you can do is to model that PFR reactor that I ask you to try to solve for the volume in that 4.2C. If you model that reactor and you make that volume really large, please see what happens to my conversion as a function of the volume, to see whether you need to believe me or not, or what I'm going to show you on the next slide. You can't force you can't force the reverse reaction to occur, because on its own it's not going to. This is going to stop, so it can't pass that point. This is the shall not pass here point. So I can't suddenly say, oh, the reverse reaction is going to take place, and now suddenly stuff is going to cool down because that is endothermic. That is not going to happen. I need to, from an external source, disturb the equilibrium condition here, not from within the reactor itself. Okay, so let's just go to a whiteboard. Right, so let's see how this is going to pan out. So I've got my X versus V that I asked you for. What do I want to see that you understand by asking this question? First of the following, the energy balance. So this is in a plug flow reactor. Sorry, the mole balance. We'll say that dFA along this length is equal to the rate. Everybody happy with the mole balance? I can now write this because I'm interested in what's happening with X along the volume. So hopefully you will all be able to translate that, to do the math, to write this as FA naught dx dV is equal to negative RA. Right? So negative RA is going to give me a positive value. So this FA naught, that is a constant. That is a constant because it's your inlet conditions. So what this expression tells us is that the slope of how x changes with v is directly proportional to how the rate changes. That's a direct proportionality. This is what I want to see illustrated on your figure. For instance, if the rate is equal, if the rate is constant, if there is a constant rate, what this means is x will increase linearly with v, because what happens to the slope? Del x over del v, del x over del v, del x over del v is going to give me that constant rate. A shape like this tells me that the rate does not change along the volume of the reactor. So it stays constant. At this point and that point and that point, I observe exactly the same rate. If the rate goes to 0, so if this happens, then I must have a 0 slope. Delta x over delta v, delta x over delta v must be equal to 0. If I want to see whether I can have an increase in the rate, so let's say x over v, an increase in the rate will therefore mean that the slope is increasing. That delta x over delta v is increasing, increasing, increasing. But now what I want you to show me that on that diagram is what do you expect for an adiabatic reversible reaction that takes place when it's an exothermic reactor. Reaction in an adiabatic reactor, sorry for that. So if you now look at the rate plot that we have, and remember it's the inverse, or let's just do the, now I can't type delete, let me delete this. If I have this rate, just the rate, so it's not the inverse of the rate. It's going to increase to a maximum and it's going to drop to 0. Right. So there is definitely a maximum in the rate. I want to see that. I want to see the fact that you can see that there's an increase in the rate and that there's a decrease in the rate when you construct your x versus v diagrams. I also want to see the following, the equilibrium limitations of the 3 different temperatures. So I know this is the colder one. It's going to, so this is going to, no, let me just delete that again. Let's have it. Oh, must find a solution for this whiteboard. So x versus volume. So the colder one is going to go the furthest because this is a reversible reaction. So if I think about my cold temperature, there, it's going to go the furthest in terms of my equilibrium limitation. If I think about the less cold one, it's going to go slightly there, and the warmest one will achieve the lowest equilibrium conversion. So this is my limits. But this one is going to get there slower, faster, and even faster. What I want to see in each case, so let's just do the red one first, is initially there will be an increase in the rate due to the temperature effect. Then I am going to see the rate starting to decrease, and boom, it's going to go to 0 when it achieves that equilibrium conversion. Let's just inspect the slopes. So I've got an increase in the slope. I've got an inflection point, and that inflection point should correspond to the point where that rate goes to a maximum. So this corresponds to that inflection point where it starts, where I have a maximum in the rate. I will see an inflection point on my x versus v graph. And then the rate just decreases. So inspect what happens to the slope. The slope will decrease quite fast until it goes to 0 when equilibrium has been achieved. And now let's go to our colder one. So the colder temperature is going to have that same increase in the rate, but the rate is going to be lower. So the slope for the colder one must be lower than the slope for the warmer one because the rate is less. Up till the point where this one can actually go past and it's going to achieve a higher equilibrium value. And the blue one, even slower, but it's going to have the same kind of inflection point where the rate achieves a maximum and then it drops to that 0 value. The slope becomes 0 when the rate goes to 0. So at this position, that is where the rate goes to 0. So for each of my 3 figures, I could actually construct a corresponding or a complementary right versus X graph, right versus X graph, for the blue one, for the red one, and for the orange one. And for each of them, that inflection point is going to be at a different position, and the equilibrium point where it intersects that X is equal to 0 line is going to occur at a different X value. So for each adiabatic operating line, I can construct a right versus X graph because I know how my temperature is going to change with X from my energy balance. And from my mole balance, I must realize that dx dv is directly proportional to negative of the rate. Okay, how's that? Questions? Those who had questions about this figures. Did you get it right? Could you read my mind or not? Anyone? Yes, Philip, go for it.
Ma'am, how would that graph look different if it was endothermic? Would the slopes just be much steeper, or would there be another difference as well?
Okay, so let's discuss the endothermic reactions because that was another question that I had. So if we look at our rate equation for endothermic reactions, all right. Okay, and I've got my K concentration, K over Kc, the concentration of B. Okay, so energy balance, X, it's a X T, and so we've got this equilibrium figure. So this is how the equilibrium line, X equilibrium for the endothermic reaction. The energy balance for adiabatic, so we're busy with adiabatic reactors for now. T naught, there we go. So with conversion, the temperature is going to decrease. With a decrease in temperature, this rate constant is going to decrease. And this is going to decrease. This is going to decrease. So in other words, I am going to have, whatever I do, as I convert in an adiabatic reaction, I'm going to have a decrease in the rate. Right. So now Philip's question is, if I now asked you for the 3 different temperatures, so this is now warmer, colder, coldest. So let's just redraw that figure for our 3 temperatures. Clear pencil there. And this is now for an endothermic reaction, X, and this is along the volume of my reactor. And I want to see what happens to this slope. What happens to the slope, which is directly proportional to min or I. What did we just say? This is going to decrease. So just for one specific inlet temperature, what I know is I will not see this increase followed by a decrease. I will just see a decrease in the rate, in the slope, decrease, until it will go to 0. Right, but for my 3 different temperatures, so this is just a generic one, for my 3 different temperatures, for the warmer one, it's going to go further, for the colder one, there, and for the coldest one, there. It's going to stop there. The coldest one, the rate is going to start off lower and it's going to decrease. So it's going to go, right? The slightly warmer one, the rate is going to start off with a slightly higher slope because I start at a higher temperature. But from that position, once again, it is going to decrease. And if I've got my high temperature one, it's going to get there faster and it's going to go the furthest. So an endothermic reaction is the best kind to work with because it plays along. And that's why we don't spend so much time evaluating its properties, because if I increase the temperature, everything works in my favor. When we design reactors, we tend to want to operate at higher temperatures because we want to increase our rate. And for an endothermic reaction, that works because we also can achieve a higher equilibrium conversion. The problem comes with the exothermic reactions, where an increase in temperature may increase the rate initially, but then due to the reversible nature of the reaction, I observe this behavior where I have the maximum and a decrease in the rate. And we don't want to size reactors when we are there. We want to size reactors trying to optimize because we are interested in minimizing that, or minimizing the amount of catalyst we have to use. If I want to minimize that, I must ensure that I operate at the highest possible achievable rate, taking into consideration lots of other stuff, like I mustn't have fouling on my catalyst, I mustn't promote any sudden side reactions by increasing the temperature, etc., etc. Does the figures, do the figures make sense to you, Philip?
Yes, thank you. That clarifies it a lot.
Okay, right. So that brings us to the next question. Let me just share my slides over here. Back. About the shape. Let's just close that. What is fouling? Not fouling. Fouling. Catalyst. So what fouling of the catalyst means, and that especially happens if you have any carbon compound that reacts. Any carbon compound that reacts, the chances are there that you can, in some side reaction, you can form carbon as a solid. And that is especially at higher temperatures and higher pressures. And that precipitates on your catalyst surface. So if you have a catalyst and you have all this beautiful active sites, now suddenly you've got a soot layer covering it. And that catalyst becomes like a dead weight in your reactor. So it cannot contribute to any of the action that's taking place in your reactor. Okay. Right, so sorry, it's not owling, it's fouling. Okay, so I had some questions on how does this figure look for an endothermic reaction, okay? So for an exothermic reaction, we don't have to guess this, we can think it out. We can think about what's going to happen to the profile. So for an endothermic reaction, this is, of course, going to look like that, my equilibrium line. Equilibrium line is going to follow this kind of shape. And, of course, this is temperature. And now for an exothermic reaction. So let's consider the X. I'm going to use red for the exothermic reaction first. For a specific concentration value, as I increase the temperature, so one fixed conversion, as I increase the temperature, I am initially going to see an increase in the rate due to the increase in temperature effect. And as I now continue along that, I see an increase in the rate, and then it goes to that maximum, and then suddenly I see the drop in the rate due to the concentration effect of the reverse reaction. So for each X, I will see an increase and a decrease due to the temperature effect, the increase, and then the decrease. That is for the exothermic reaction. But let's just see what happens to our endothermic reaction. Let's just take 30% conversion. So that's the concentration I work with. And now you should ignore these lines. What is going to happen to the rate as I am going to increase the temperature? What is going to happen to the rate as I increase the temperature? The concentration stays the same. It will just increase. There's not going to be that drop in the rate. It's going to increase. There's not going to be the drop in the rate due to the reverse reaction that suddenly becomes. It's much easier actually to visualize this when you come from the cold side. So if I start at the cold side, and I increase the rate, I'm going to start at a lower rate and it's going to increase. So for an endothermic reaction, I am not going to have these iso rate lines that come back down. It will rather be the low rates, and then I'm going to see an exponential increase here with temperature as I increase my temperature. So I will not have this duplicity in the rate that I have for an endothermic reaction. Let's just evaluate the adiabatic operating lines. For an exothermic reaction, the adiabatic operating lines will go like that. So I will see an increase in the rate due to the temperature and then a decrease in the rate due to the concentration effect. For the endothermic reactions, I am just going to see a decrease in the temperature. So I'm going to start at my high rates. The rate is going to decrease because of temperature and because of the drop in concentration because of the increase in conversion. So the only thing we'll see is a constant drop in the rate until it goes to equilibrium, where the rates are bunched up and I really drop there in terms of my rate. So the figures actually in terms of the ISO rate lines look completely different. I just have a different shape for my ISO rate lines on the endothermic reaction scheme. Okay, so let's see, questions on this. Anybody wants to put up a hand? Shapes, nothing. Going. Okay, please repeat. Okay, for the endo, let me just get a clean page so that we don't have the confusion of the exothermic reactions clouding our view. So for an endothermic reaction, X, this is temperature, and this is my X equilibrium line. The energy balance goes in this direction because with an increase in conversion, the temperature is going to drop because of the endothermic nature of that reaction. Right. So as I increase the conversion, two things happen. The concentration of my reactant A is going to go down. The concentration of B is going to go up. The net effect of only considering that part of the change with X will be that I will see a drop in the rate of my forward reaction. Right. In addition, what is going to happen? The temperature as a function of X. As I increase X, the temperature, which is over here, temperature goes down. And the net effect of that is also a drop in the rate. So if I have my ISO rate lines over here, I will therefore have the highest rate lines. And as it goes down, I am just going to see a drop in the rate. So the ISO rate lines here will be the high rates, and that is going to go to the lower rates over there for the adiabatic endothermic reaction. So if I should plot this on a min RA versus X figure, what is going to happen to my rate is that I'm not going to see this adiabatic, let's just that I see for the exothermic reaction, that it's got a maximum in the rate. This rate is just going to drop, start at a point, it's going to drop, and then it's just going to go to zero quite suddenly. It's a very faster drop. The slope of the change in RA with X becomes more significant as I approach the equilibrium conversion line. How's that? All right. Any more questions? We've got 10 minutes left for this session. Before I just briefly want to say something, then we have some, where do we operate? Exothermic reactions, we would operate at a maximum. Where do we operate for endotherm? Right, so for endothermic reactions, we would like to operate as warm as possible. And so as warm as possible will mean that we need to take, so the warmer, the better. There's no maximum. There's just the warmer, the faster, and the further. So that's a win-win situation. However, we are going to be limited by that Owling thing of the catalyst. And also, when we have a real-life reactor that we're going to design, we have maybe A that goes to B, and then we can have B that cracks to form C plus D, and this we don't want. So we increase the temperature and we increase this rate, we increase the temperature, but then we also increase that rate. And this cracking reaction maybe have a higher activation energy. So it's more temperature dependent. So I increase this rate, but I increase the rate of my unfavorable reaction, undesirable reaction even more. Meaning that my selectivity of B divided by C plus D, the product flow, will drop with an increase in temperature at a certain point. Because if I am at a lower temperature, I can just have this reverse reaction taking place due to the high activation energy of the competing reaction. But now if I suddenly increase the temperature, this thing will become significant. So for endothermic reactions, the factors that we need to take into consideration is not only operating at a relatively high rate, because that I can achieve with high temperature, but rather what happens to the competing reactions that I have in my reactor. Selective or not necessary for the semester test. We are going to do a big TAT on after the semester test that will actually be formulated as an assignment on a real life reaction scheme where we've got lots of competing reactions, and you will be asked to calculate selectivity as a function of different operating conditions. So watch this space. Just survive the semester test week first. Okay, so is dodgy. Okay, so selectivity is using concept, but multiple reactions, not in terms of the energy balance. So, you know what? Let me be honest. There is no multiple reaction question in the test because I ask energy balance kind of questions and the Ergen equation, and therefore I will not subject you to multiple reactions in this test. Okay, cool. But I just share in slide plots top. Oh, now there it disappeared. In the slide, in the second page, the plots on the graphs on top of the EB lines, and then the reaction rate. Oops, now I have to open the slides. Share. There we go. Possible? No. There are no good sources. And even the good sources can sometimes confuse people. So the sources are, you have to read up you have to do a proper literature survey, and that's going to take a big part of your first part of your design process is to find out which competing reactions do actually take place and which catalyst prevents the competing reactions from taking place and favors just the reactions that you're interested in, and what's your temperature range that you want to work with in order to avoid side reactions or to favor the reaction that you are interested in. So let me just share this, and he says on the second page, okay, so let me just get that question up again. On the second page, this plots on the graphs on top of the page are EB lines, and then the reaction rate equations plots right. Just below the reaction rate equation. So I am not there. Okay. So are you talking about these equations? So both of them are, this is just the inverse of right, and this is just what I recommend you do when you plot this in Python, is instead of, because depending on your lens space values, you may actually have exactly a value there where your right goes to 0, and then you're just going to give a pink screen because it's going to complain that you are dividing by a 0. So it's safer to construct your Levensspiegel plots by considering the rate just as without dividing by 0, because we are not going to use the constructions in order to size our different reactors. We are going to model it, we're going to find the maximum in the rate, etc. I'm not sure whether I answered your question, Luca.
Sorry, Leslie, can you hear me?
Yes, I can hear you. Thank you for speaking.
No problem. I just wanted to find out, sorry if this is a stupid question, I just wanted to make sure. So the top plots for the exothermic and endothermic plots.
Yes, yeah.
Versus temperature. That red line and blue line, is that the lines representing the rate equation?
No. This is not. So don't confuse this with your mole balance for your CSTR. The mole balance for the CSTR, please plot this when you are doing the TATs. In a CSTR mole balance, the equations look like this. For an irreversible reaction, the CSTR mole balance looks like this. Still, where it intersects, that is our operating point. However, for the mole balance for a CSTR in a reversible reaction, it realizes that it can't pass that point. It's so cute if you do that actually and you plot it. Is that it goes up and then it goes down again. So that's the mole balance, and wherever that intersects, the adiabatic operating line will still be the operating point of your CSTR reactor. You can still get multiplicity, even if you have a reversible reaction. You can have multiplicity, it can operate there, there, and there. Ideally, if you've sized your reactor well, if you've done your job well and you want to size an adiabatic reactor, that point where there's therefore a maximum possible conversion that can be achieved in any size or flow rate CSTR reactor. If you size your reactor properly, that intersection of your adiabatic line will coincide with that maximum possible conversion that can be achieved in that reactor. You can do a horrible job, and you can have a reactor that's got this size, and this is your energy balance, and you do not fully utilize the potential of your reactor because you operate at a lower conversion that can actually be achieved by manipulating your energy balance. Okay, does that make sense?
Yes, that's perfect. Thanks, Gillespie.
Okay, thank you for that question. So remember, this line is an add-on. We had the different lines that we can plot for a CSTR. Just to share a blank. Well, there we go. For a CSTR, we now have 3 different lines that we can plot. We've got our equilibrium line. X equilibrium line, thou shalt not pass here. We've got our energy balance line that says this is the maximum possible if this is my inlet temperature, and I can manipulate that still by having a utility that cools or heats up that's going to shift as well, the intersection point. So that's the energy balance line, and then in addition I have that two mole balance lines that we use to solve what the operating point is if I have that adiabatic operation in my CSTR, or non-adiabatic by changing the slope and the intercept of my energy balance. So for a CSTR, 3 lines: mole balance, energy balance, thou shalt not pass. Right. Sure, I think that was a mouthful. At 2, is this a satisfactory? Yuck, sorry, there it disappears. Since 2 or more, is this no? No. So the fact that this is true, shucks, I'm keeping you a bit long. The fact that this is true, if I look at my right equation, x, yes, definitely. No, not sorry. This is actually a good question. So if I look at my ISO right lines, for each x, what he says is I can have 2 different temperatures where I can find exactly the same rate. That is not an indication that you have multiplicity. So that just the fact that this is possible is not an indication. You still have to plot your mole balance versus your energy balance. And if these 2 lines, the red and the blue one, if they, for instance, show something like that, then you have multiplicity. But the fact that the rate comes up and goes back down, and that you can, for the same x value, get the rate at 2 different temperatures, doesn't say that you have multiplicity. You still have to have your mole balance and your energy balance plot to confirm that. Okay. Right, I will stick around for a bit if you've got more questions, but I'm going